In section 5.3, let's discuss determinant solution of linear systems. Now, associated with every square matrix, there's an attribute called determinant. So I want to emphasize to begin with that we have to have what we call a square. I'm not happy with my square. We have to have a square matrix. So what is a square matrix? Remember, a matrix is a rectangular, not a square, rectangular array of numbers. So if the number of rows and columns in the matrix, if the rows are equal to the number of columns, then the matrix is called a square matrix. So suppose I have A, B, C, D like that. This is a 2 by 2 square matrix. 3 by 3, 4 by 3, and so on. So that's what a square matrix is. Now again, one attribute or associated with every square matrix is an attribute called the determinant of a matrix. So what does this determinant look like? Suppose I have a matrix in general form. My matrix A has elements first row, first column, first row, second column, second row, first, and second. Suppose I have that. Now, the determinant of A, which looks like the absolute value symbol, so we use the vertical line here as the notation for determinant. So this would be determinant of matrix A. Some textbooks also, and myself included, sometimes use DETA. I think that's more descriptive. This is just so it doesn't confuse us with the absolute value notation. So please do not interpret the lines here as absolute value of a matrix, because determinant could be negative. So for example, determinant of matrix A could be negative 20. So it doesn't mean absolute value. All right, maybe a poor choice of notation, but it is what it is. So how do we find this infamous determinant? Well, determinant of matrix A for the 2 by 2 is actually pretty straightforward. You do A11 times A22 minus A12 times A21. Okay, well, what does that look like? Well, A11, A22 means you multiply these two elements and then subtract the product going in the other direction. You multiply the diagonals minus product of off diagonals. Sometimes, again, we may use this kind of a symbol to help us remember how this product goes. Okay, notice I went from A11 to A22 and then kind of curved around and came back to A21. That's the direction of the product that takes place. The minus has to be there. You subtract the off diagonals, the product of off diagonals from the product of diagonal elements. Now, what does a 3 by 3 determinant of a 3 by 3 looks like? And that's what we're going to spend time on mostly, because 2 by 2 we have a formula. There are formulas for 3 by 3 also, but this is what we want to know. We want to know how is determinant of A if A is now in this form. Let's say I have the elements first row, first column, first row, second, first, third. Notice I'm using subscript here, by the way. Subscript notation for the elements of the matrix. So this would be A23, and then this is A31, A32, and A33. There you have it. Okay, suppose I have that. How do we find the determinant of a 3 by 3? Now, the method that we're going to use is called expansion by cofactors. All right, so before we actually see how this expansion by cofactors would look like, let's define what we mean by a cofactor of a matrix. So what I have copied here is definition of a cofactor. The cofactor is defined as let M subscript ij be the minor for element. Need to define what a minor is here in context of matrix. Minor of element aij in the in an n by n matrix. Remember, for determinant, the matrix must be square matrix, means it has to have n by n. Its dimension has to be n by n. Same number of rows and columns. The cofactor of Aij, remember Aij is an element of the matrix, right? So the cofactor of an element of a matrix is defined as, call this Aij as a cofactor, is defined as -1 to the power I plus j times the minor of the element in that row column position. Now, a note about the sign here, -1 to I plus j. The I and j, by the way, here are the subscript for row and columns. So, for example, when we go I 2, 3, that means second row, third column. That's just what the subscript means. So if I look at -1 to the power of, this is ij, that means you add the subscripts, 2 plus 3. That's -1 to the 5th power, and that's -1. So what you get out of this factor in front is either a +1 or a -1, always. Okay? So keep that in mind, because later on I'm actually going to create a sign chart for just -1 to the power. Now the minor of the element, let's talk about that one. Let's talk about the minor of an element of a matrix. And for simplicity, I'm just going to make this matrix, let's say matrix A, I'm going to make it a 2 by 2. Suppose this is 3, 4, -1, 5. Okay, and let's say we want to find the minor of element, minor of 3 here. So I want to find M1, 1, the minor of element in the first row, first column, minor of 3. The minor of 3 in this case is the matrix that remains. In this case, it will be just a 5, and I'll show you why. That we obtain by deleting the row, deleting the column in which that element appears. Notice when I literally delete means you remove it. Delete the row and column, what that remains is a 5. So in my 2 by 2, the minor of 3 is 5 in that position. Okay. What is the minor of 4? 4 is in the first row, second column, right? You delete the row, you delete the column in which 4 appears. The minor of that is -1. See how easy that is? What is the minor of 5? That's the element in the second row, second column. You delete the column, the row in which 5 appears, and you get 3. So that's all a minor is. Okay. Now, what if I have a 3 by 3? So for example, let's say matrix A, I'm going to make it 1, 2, 3, -1, 0, 5, 4, 7. Let's do another 3 also, just to make a point here. And suppose I want to find a minor of 2 in that position. So the minor of the element in the first row, second column, right? First row, second column, which is a 2. You delete the column and you delete the row in which 2 appears. The remaining matrix is -1, 5, 4, 3. All right, it's a matrix. So that's minor of 2. Let's do minor of 3 in that position. The element, the location of 3 is in the first row, third column. So you delete the row, you delete the column in which 3 appears in. The remaining elements of the matrix are -1, 0, 4, 7. There we have that one. All right. And let's do minor of this 3. See, they're both 3s, right? But they appear in different locations. So their minors are going to be totally different. So if I look at M, this time 3 is in the third row, third column. Minor of third row, third column, 3 in that position, is when you delete the row and the column in which 3 appears in that spot. And I get 1, 2, -1, 0. There you have it. See how that works? And there And that would be the minors. Now we do something with the minors going forward, but I just want to clarify what that minor is. So let's actually do find the determinant using expansion by cofactors. So let's say I want to find determinant of A, where A is given by, it's going to be elements of a 3 by 3. Okay, so I'm going to have first row, second column. Got to be careful there. First row, third, second, 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 third, third, second, third, third. Okay, so let's try to do this. So here's how it works. Because we have 3 rows and 3 columns, so I can do expansion, find the determinant using expansion by cofactors 6 different ways. Okay, and the question, let's say find the determinant. So there, if I want to give you a formula, we could give you 6 formulas. The book gives you 1 formula, by the way, but I'm just going to show you how this is done in general, and we go to an example to test it out. So the formula, I believe that's in the book, they do expansion by cofactors about the first row. So let me do that. Let's say I want to do use cofactor expansion to find the determinant. Expansion about the first row of this matrix. Now the cofactors, remember we have these elements, right? These elements A11, A12, A13. Therefore, the determinant of A is going to be the cofactors. Remember the cofactor up here, we use the A sub ij. Okay, so we're going to have the element times the cofactors. So it's going to be, the cofactor would be A11 times A11. Remember, this is the cofactor. Okay, and then we go plus the cofactor in the first row, second column, times the element in the first row, second, plus cofactor, first row, third column, times the element in the first row, third column. Again, the capital A's are cofactors, the little a's, these are the elements of the matrix. Okay, and that's how it's done. There's your formula. That's for the first row. I could do it about the third column, and so on and so forth. I just want to do, I don't want to overwhelm you with all of these formulas now. So let me just give you an example. It's easier done with an example. And in the example, though, we do it using expansion by different rows or columns. Okay. So in my example, let's do this. Suppose my 3 by 3 matrix A is the following. Let's say it's -2, 0, 1, and then 1, 2, 0, 4, 2, 1. And we want to do this determinant. We want to find the determinant. Now, I'm going to expand about the first row, this formula. Expand about the first row. So what do I need to do? Well, I need to do -2, that's A11. So it's going to be -2 times A11 plus 0 times A12 plus 1 times A13. Okay, so I have the elements multiplied by the cofactors. Now let's find cofactor of A11. The cofactor A11 means the element in the first row, first column, that cofactor. The sign, first of all, this is going to be -2 times, the sign is -1 to the sum of the subscripts. Remember, you add the subscripts, you put them up there. 1 plus 1 times minor of 1, 1 plus 0 times that is 0. So let me not bother with that. 0 times any number is 0. These cofactors and minors end up being real numbers. 0 times any real number is 0, so we're going to skip that one. Plus 1 times negative 1 to the power of 1 plus 3. Remember, the subscript is 1, 3. So we're going to add 1 plus 3 times minor of the element in that row in the 1, 3 position. Let's see what this is going to be now. Next, so we're going to go negative 1 to the second power, right? Negative 1. 1 plus 1 is 2. So negative 1 squared is just 1. That's negative 2m11. And negative 1 to the fourth power is positive. So it's going to be plus 1 times m13. Now we got to do the minors. Remember how I did the minors earlier? You delete the row column in which the element appears in. So minor of element in the first row, first column. You delete the row, you delete the column in which that element appears in. So that's going to be the determinant, right? The determinant of 2, 0, 2, 1. Again, for the minor, the minor is the determinant. Let me fix this here too. This is going to be the determinant of these. Okay. I was just showing you what the matrix was, but these are actually determinants. So each of these we should find, right? And I'll show you in my example how we find them. The minor of element in the first row, third column. Let's do that one. That one is going to be, let's see, I just deleted something that was negative 2, right? Okay. The minor in first row, third column. You delete the column, you delete the row. And it's going to be the determinant of a 2 by 2, 1, 2, 4, 2. So we have negative 2 times that determinant plus 1 times that determinant. Now the determinant for the 2 by 2, remember, we multiply the diagonals. 2 times 1 minus 0 times 2, the off diagonal, plus 1 times, you multiply the diagonal, 1 by 2 minus 2 by 4. A lot of detailed work, huh? It's not hard, it's just tedious. It's all arithmetic. That's going to be 0. So it's negative 2 times 2 plus 1 times, this would be 2 minus 8. And that's negative 6, negative 4. Negative 10 is going to be the determinant of this matrix. And we will verify it, we'll confirm it using expansion by another row or column in just a moment. Now, we will create a shortcut here in a moment. Okay, so this will go a little faster. So that's the determinant, and that was the method of expansion by cofactors. Now, let's do exact same determinant. You want to find determinant of A. This time, I'm going to expand about the second row. Okay, now the sign on the cofactors, right in here, we can actually create a sign chart, so we don't have to bother with that part in our formula in here and in here. Okay, so here's what the sign chart looks like for a 3 by 3 matrix. This is negative 1 to I plus j. Okay, only the sign on the matrix is going to be plus, minus, plus, minus, plus, minus, plus, minus, plus, right? Those are the signs that we need that get multiplied by the minors. So this way now we can kind of create a shortcut. We don't have to do negative 1 to a power. Let's do expansion about the second row. So for that, we're going to get the signs from the second row. Determinant of A is going to be the elements in the second row are 1, 2, and 0, correct? 1, 2, 0. Those are the elements. So I wrote the elements. Now, the sign, we attach the signs here. We put negative, positive, negative. So we did negative 1 to the I plus j, in other words. So we do the elements, then the signs. Now we can do the minors. Okay, let's do the minors. The minor of 1 in that spot. You delete the row, you delete the column in which it appears. So what do we have? We have a determinant of a 2 by 2 of the remaining elements 0, 1, 2, 1. And here's another determinant, here's another determinant. All right, so that was the minor of 1 in that position. Next, we need to do minor of 2. You delete the row and you delete the column in which 2 appears. The remaining numbers are, let me make room here. It's going to be -2, 1, 4, 1. And then this was minus. The element is 0. We're about to do determinant of that. And of course, that's going to be the product of 0 times whatever the determinant is 0. But I just want to go through the motions in trying to find the minors. So you locate the element that you want the minor of. You delete the row, you delete the column. The remaining numbers are -2, 0, 4, 2. So for the 3 by 3 systems, every time you do this, the minors are going to be determinants of 2 by 2s. Now let's find the determinant. -1 times determinant. Remember, we go in this direction. 0 times 1 is 0, minus 1 by 2 is 2. I'm using the formula that we had. Plus 2 times. -2 times 1 is -2, minus 1 by 4 is 4. So there you go, that's the determinant there. 0 times anything again, let's spare that one. That's just 0, we don't need to write that one. Okay. -1 times 0 minus 2 is -2, and 2 times -2 minus 4 is -6. Negative is +2, -6 by 2, -12. And the sum is -10, and there is your determinant. Notice we got it to be the same up here. So it doesn't matter which row and column you expand about. Now we can be easy on ourselves, right? The recommendation, by the way, is to expand about the row and column with the most number of zeros. In my made-up example, I only have 0 in the first row, second column, and I have 0 in the first, second row, third column. So expansion about the second column would be good. Expansion about the second row, which we just did, is good also. And there you have it. So let me just annotate this, that here we expand about row 2. That's what we did here for this part. The first part, we expanded about the first row. We expanded about the first row here. Okay, and there you have it. Again, pretty easy if you kind of keep it in an orderly manner. So let's do another one, and let's see if we can make this go a little faster. Okay. How much detail you need, by the way, how much detail you put into this is up to you. It's all arithmetic. So I'm sure some of you that are quick with arithmetic can find ways to make this go a little faster. And there you go. So for this one, again, let's expand about the first row. Remember about the first row, I need to grab the signs. That's plus, minus, plus the signs. So we're done with the powers of -1. Then the elements. The element in the first row are 10, 2, and 1. Each of those multiplied by the minors. So let's now begin. Minor of 10. Delete the row, delete the column. So I'm going to get the determinant of 4, 3, 8, 10. Done with this one. Let's look at minor of 2. Delete the row, delete the column. That's a determinant of -1, 3, -3, 10. Done with that one. And finally, minor of 1 in the first row, third column. Delete the first row, third column. The remaining elements, -1, 4, -3, 8. So we just have to find that 2 by 2 determinant. And this becomes 10 times. 4 by 10 is 40 minus 24. Once you get down to the 2 by 2 level, then determinant is easy. Remember, you multiply the diagonals minus the off diagonals. Plus, next one, multiply diagonal minus the off diagonals. That will be 10. 40 minus 24, that's 16. Negative 2 times. Negative 10 plus 9 is negative 1. Plus negative 8 plus 12, that would be 4. And that's 160 plus 2 plus 4. Unless I made arithmetic mistake, that determinant should be 166. And by the way, these TI graphing calculators and other calculators will give you the determinants, so you can always check your answer this way. All right, and let's do another example. This time, suppose I have, let me make one where I have an entire row or column of zeros, don't matter. I'm going to make the row 0. Notice, so this is really like having two equations. Two equations. Well, this is, never mind. But anyway, a row is 0. So if I expand about the second row to find that 3 by 3 determinant, what am I going to have? Well, the sign for the second row is minus plus minus, correct? So I'm going to go minus plus minus. But then each element in that row is 0 times its own minor, right? Minor of second row, first column, minor of second, minor of second, third. Don't matter what those determinants are. Each of these would be 0. So that determinant is going to be 0. In fact, there's a whole host of property of determinants that we could cite here, but not necessary. This is good enough for us. So if every row or column is 0, determinant would be 0. Determinant of A is 0 if this is determinant of A. All right. Now let's talk about Cramer's method, the last idea of this section, or Cramer's rule for solving systems. Cramer's rule, I'm going to state Cramer's rule for just a system of equations where we have 2 equations, 2 unknowns. Because again, we're not going to be using this rule going forward. Just to give you exposure to the name and the method is all we want here. The Cramer's method applies to larger systems, by the way, 3 by 3s, 3 equation, 3 unknown, and so on and so forth. Now, so we have a 2 by 2 system here, right? 2 equation, 2 unknowns. And what Cramer's method does, it actually gives you the solution to the system. It's kind of like a canned product, okay? And here's what the solution to the system is. X is equal to d subscript x capital D, and y would be d subscript y over capital D here. Now, what are the d's here? The capital D here is a determinant of the matrix of coefficients, A2, B2. And dx is the determinant of a matrix that you get by removing the x column, replacing it by matrix of constants, C1, C2. And there you go. That's what dx is. The subscript x reminds me which column to throw away. So dy, I throw away the dy, means the y column in D. Keep A1, A2. If I throw a column, I need to replace it, right? What do I replace it by? By the column of constants, matrix of constants, we call them. And there you have it. That's all it is. Again, it reminds me of the quadratic formula for solving quadratic equations. Now, the assumption, of course, because you're dividing by D here, right? So the assumption is that D is not 0 in order for this to yield a solution. If D is 0, let me put that as a note. If D is 0, what would that mean? That means the system is either dependent or inconsistent. In other words, you could have infinitely many solutions or no solution. All right. So, and what happens if that's the case? Then we use another method. Simple. Now, let's take a look at example. Suppose in my example, again, we just do an example of this. One is more than enough for what we do for the 2 by 2. So I have x plus y equal 4. The other equation is 2x minus y equal 2. And let's form our d dx dy. Remember, d is the determinant of a 2 by 2 matrix of coefficients. Coefficients are numbers in front of xy. The x is when you throw away the x column in here, keep the second column, keep the second, and replace the first by a matrix of constants. And what about dy? dy, you look at d, keep the x column, replace the y column, right? You throw the y column, replace it by 4, 2 in there. And now I have my d dx dy. Now we need to find the determinant, right? Multiply the diagonals minus product of off diagonals. dx, multiply diagonal minus off diagonal. Dy, you multiply 1 by 2, the diagonal elements, minus 4 by 2 is 8, and you get negative 6. So there you go. We got those key numbers. Now here comes the canned product. X is dx over d. dx is negative 6, and d is negative 3. The answer is 2. And y would be dy over d. So it's going to be negative 6 divided by d is negative 3. And that's going to be 2. But just so happened the solution is x and y turn out to be the same. Purely coincidental. That's the solution to the system. See how nice and clean. For a 2 by 2, it works out really good. And even for a 3 by 3, this works. Now, let me finish this work off. Having talked about how to find determinants for a 3 by 3. Okay, let me give you now a really shortcut, turbo way of solving or finding determinants of 3 by 3. Some of you may have seen this, some of you know it and probably say, why didn't he do it this way? It's much faster. Why bother with all that cofactor expansion and all that? Well, we had to because that's what we're supposed to do. But not having done that, let's say I have a matrix and I want to find the determinant of this matrix. The numbers are 6, 2, 4, 8, 9, 3, and let's say 1, 2, 0. Okay, now what we taught you earlier still works, but let's actually do the determinant here. So how would I find the determinant? I'm going to use again the fast way of doing it. So for this method, here's what we do. We're going to actually repeat the first 2 columns. Okay, we're going to repeat the first 2 columns. So I'm going to get 6, 8, 1, 2, 9, 2. We repeat the first 2 columns. And then we're going to multiply next. We're going to multiply numbers going in this direction. So I'm going to go 6, 9, 0, 2, 3, 1, 4, 8, 2. Products going in that direction. The first product, 6, 9, 0 is 0. The next set of product, 2, 3, 1 would be 6. The next set of product would be 4 times 8, 32 by 2, 64. Okay, and then we're going to add these numbers. We're going to add them. The sum is going to be 64 and 6. That will make it 70. Okay, so hopefully you were able to follow that. Now, what do we do next? Next, we're going to look at products now going in this direction. We're going to do exactly the same thing. 280, the product is 0. 632, that's 36. And 491 is 36, also the product. And then let's add them. 36, 36, 0 adds to 72. And we're going to subtract 72 from this. So remember, you look at products going in this direction minus products, some of the products going in the other direction. So the answer is -2. And you can check to see that this one indeed works, and the determinant will be -2. So again, this is just the express way of doing it without going through all of the cofactors, minors, and so forth. But please don't do the shortcut. Okay, try to learn this as we're supposed to, even though if you just learn it for an exam or a homework. But this is how this is done. So we are done with this section. Hope everything was crystal clear and everybody's good on finding their determinants. Thank you for watching, everyone.